Okay. All right. So before I start, I want to discuss about what my plan are for the next few lectures. So first of all, Faye should post schedule for sign up very soon. So we have a number of teams for the final project. So we need to, as part of the final project, is a final project presentation. And based on the number of project we have, each project team will get roughly 15 minutes of presentation time. So of course, we cannot do it in one single day. So what I normally do is I split it into 2 days. So the first day of doing it is going to be April, I believe it's April 27, which is in 1 week and a half, roughly, or 1 week and a half. So 27 is, let's see, today is a 15. Yeah, so it's a little bit less than actually 2 weeks. So that's the day where it's a normal class time where there's 80 minutes. So then 5 teams will sign up for that day. And the next one is our final exam day. Faye, would you remind me, is it like May 2nd?
The 5th.
It's May 5th.
Yeah, it's the Wednesday after.
Yeah, so there we have two, I believe it's 2 hours, right? So 120 minutes. So there are slightly more teams that can sign up for that day. So of course there is advantage and disadvantage of each day. The April 27 dates are a bit earlier than the May 5th dates, which is our final exam day that is allocated for this class. It's earlier, but it also means you get it done earlier and you get feedbacks earlier for your final results, and then you can kind of have more time to work on your final report. If you sign up for the May 5th, it's a bit later, you have a bit more time to work on your final project, but then you only have 2 days to complete your final project report, because the final project report is due on May 7. Okay, so they both have advantage and disadvantages, and then Faye will post the signed up sheet. So each team should sign up by just putting your name, the team member's name, to the corresponding time slot. Of course, don't double book, right? Each time slot is only reserved for 1 team. Any questions? Okay, no? Then Faye will hopefully make the sign up sheet available today, right?
Yes. I'll post it in a little bit.
Okay, yeah, so that's number 1 is for sign up. And the second thing is, for the remaining lectures, today we're going to go over the remaining portion of TDA plus data sketching. I think it's a very exciting direction. There's a second half of the talk that I didn't go through. Then we want to talk about some discussion over future directions of topological data analysis. Of course, it's not going to be a comprehensive discussion, but I like to hear everybody's opinion, and then I will end today's lecture with a few more applications. And then for the following 2 lectures, what I will have, this is right before, so this is next week. So the April 20 and April 22nd. For both lectures, I actually also have guest lectures from my good friend and collaborators. One is from Liz Munch from Michigan State University, and she's going to talk about her applications of TDA over plant morphology, as well as the study of hurricane and some time series. And then the other guest lecturer will be Dr. Roxana Bujak from Los Alamos National Lab, and she will talk primarily about sort of TDA in study the topology of vector fields. That is a large area which I have not covered in this course. So this is really at the intersection between TDA visualization and topology of vector field. So those are the 2 upcoming guest lectures. So the formula is going to be, they will give the guest lecturer, and then we will have a Q&A session. And if we have more time, we'll have more discussions along the same line of applications. Okay. All right. Any questions before we start today's lecture? Okay. All right. Let's get back to data sketching. So, so this is something we covered last week. But in between we had a guest lecture. So let's give a quick overview of what's a pipeline. Okay. The pipeline of using data sketching, right? If you're looking at a large scale picture, at least for this particular application, we really have 3 goals. One is, can I find good representatives? Okay, so those are in some sense of what we call the basis trees. Those are in some sense considered as good representatives of the entire set of input trees. The second one is to say, can we use it to detect outliers? I'm putting a quotation mark to it because those outliers are in some sense outliers with respect to the basis trees, right? So in some sense that if my basis is well chosen to represent the structure variability among the input trees, then anything that is deviating significantly from those basis trees can be treated as outliers. However, if you don't have sufficient basis, right, you might pick up something that is basically considered outlier with respect to the current set of bases, but may not be outlier with a different set of bases. Okay, so outliers is in some sense are the ones with large sketch error. Okay, so essentially that they are not so well represented by those basis trees. The last one, which is basically what we call compressed representation. So what do we have? We start with n number of trees, but we end up chosen k to be the number of bases. And then in some sense, k is much smaller than n, right? So n is in the initial number of trees and k is sort of the number of basis trees. If k is significantly smaller than n, then what we have is a compressed representation in the sense that all the input tree can be now expressed as a linear combination of those basis trees. So I can represent the entire input collection by those k bases instead of capital N. Okay, so that is really large, the overview of what is the goal of this kind of approach. But now let's look at each steps, and then we'll go back to the GW framework, because that is a framework that is probably the most mathematical, and we kind of end our discussion there last lecture. So what is a framework? The framework is that in order to do sort of apply matrix sketching to complicated structures such as merge trees, the first things I need to do, which is step 1 and step 2, is to try to map the input tree to a high dimensional vector. And this mapping requires 2 things. First of all, because I'm going to apply things like matrix sketching. In order to do matrix sketching, each of the columns has to have the same size. So in other words, the first requirement of converting a merge tree to a high dimensional vector is somehow, even if my input merge tree has different sizes, I would like to convert them to be high dimensional vector of the same length. Okay, so that's one of the first constraint. However, that is not sufficient. The second thing is that if you think about high dimensional point cloud, right? Let's say one of those high dimensional point is represents a patient. So it's like height, weight, and some other measurements, okay? So if you think about it, I have patient 1 versus patient 2. They both have the same dimension in terms of what is their weights and what is their height. So that means all the dimensions have a correspondence between one another. So that's a second constraint we need to take into consideration. If we are mapping two merged tree into a high dimensional vector of the same size, we need to be aware that once I map them into two vectors of the same size, that their corresponding dimension, like for example, this is sort of the fifth dimension of this high dimensional vector that's coming from merge tree, that those have to have some form of correspondences. That is what the Gromov-Washington framework, which I call GW framework, come in, because if I translate back to the tree structure, it's basically saying that if you have two trees, that the dimension where those tree map to, for example, like this root node here versus this root node here, they have to have some sort of correspondences, which corresponding to the correspondences in the corresponding high dimensional vector. All right. Okay, so if you look at step 1 and 2, those achieve the goal together. So step 1 is to say for every single merge tree, I'm going to treat it as a what's called metric measure network, which we're going to see very soon. We're going to treat it as essentially there's a probability distribution over each of those trees. The second one is when I vectorize it, which means making it to a vector, there is essentially the process of blow up, which makes them to be of the same size, alignment, which is making sure their dimension correspond to one another, with respect to what's called Fauché mean. So Fauché mean is essentially a structural average of the entire input collection of trees. So the Fauché mean tree has a particular size. So every input tree is going to be matched to that same size, and their features is going to be aligned to the mean tree. So that guaranteed both constraint, as I just described, they are having the same vector set length of the vector, and their features correspond to one another. Their features actually correspond to one another by corresponding to their mean tree. So that's a step 1 and 2. And then step 3 is just applying, once you converted the tree into vectors, you combine the vectors together to form my data matrix. And then I'm just going to apply matrix sketching techniques. And you can do a number of matrix sketching techniques here. Okay, so the framework is very general. And then step 4 and step 5 is basically saying that, well, now I have factored my matrix where A is approximated by A hat, which is approximated by B times Y. Then for each column of B and each column of A hat, now I can convert the high dimensional vector back to a tree representation. Okay, so let's go through every of those steps. The first step, as I mentioned before, is, I'm going to erase those so that it's not overwhelming. The first step is to treat each tree as a measure network. Okay, so if you think about a merge tree, what information does it have? Of course, it will have its vertex set V, right? What are the nodes? It also has what's called the weight matrix. So the weight is basically saying that between every edges in the merge tree, what are the weights attached to it? And then the last one is a probability over the node set. Okay, so of course in here we're treating W as a pairwise distances. In general, it can be treated as a weight. Okay, and then P is a probability distribution. Okay, so the first thing we do is actually P is a uniform distribution, which means that every single node in the tree is going to have the same probability. So for example, if the tree has 4 nodes, then every node has a probability of 0.25. So it's actually a probability distribution over the entire nodes. So for example, if I have this very simple merge tree, it only has 4 nodes. So the number of node is equal to 4. Then the probability distribution over each point is going to look like 0.25, 0.25, 0.25, and 0.25. This is a one-dimensional vector. Okay. Now, W, what I say is says as pairwise distances. but in a way that, generically think about as a weight matrix. And in the original GW framework, it can be coming from anything, maybe coming from prior knowledge. For example, if I have a network, a social network involving people emailing each other, then the weight can be number of emails they exchange with each other within, say, a day. But in this particular case, because we care about merge trees, what we want to consider is to say that I would like the weight to capture the underlying structure of my merge tree. So one way to do it, what's differentiate merge tree from any tree structure is, in fact, there is a height function defined, well, not necessarily height, but there's a function defined on the merge tree, right? Because merge tree is coming from sub-level set filtration of a function over domain. So now that means every single node has a corresponding function value on it. So that is, for a pair of node x and x prime, there is a height function. There's a function value defined on it, which is fx and fx prime. So if they're adjacent to each other, this weight is the absolute difference between their function value. And then if they are not adjacent to each other, let's say x prime and x double prime, they're not adjacent to each other, then this w between them is the shortest path based on this weight. Okay, so now what happened is that I have already specified for every single input tree the probability distribution over the nodes and its corresponding weight matrices. Okay, and the weight is encoding some information coming from the merge tree themselves, which is related to the function on the nodes. Then what we can do is to say, now I need to vectorize it. So in order, before we vectorizing, I actually need to make sure all those trees can be mapped to the same vector of the same size, and then there's correspondences. And then this is exactly where GW framework comes in. So on the high level, if you have an input tree 0, tree 1 up until, say, tree n minus 1, this is a collection of trees that you input. What you do is you compute the average tree, and we'll get back to the GW framework very soon. So let's say you have a way to compute this average tree. Then the idea is to map every single tree against this average tree. Okay, so when you match it, it's through this GW framework, meaning that if I have a bunch of nodes in my average tree, let's say my average tree has, let's say this is size 20, right? Size 20 meaning it has 20 nodes. So then, let's say input tree 0 has size, let's say 8, okay? So of course, the average tree is typically much bigger than all input trees. So if I want to match an input tree to this average tree, and average tree is bigger, what is the thing you're going to do? You are essentially trying to duplicate labels or nodes in the input tree. So in some sense, if the input tree, the first zeros tree has 8 nodes originally, you are going to sort of duplicate some of those nodes such that it will end up carrying all the 20 nodes from the average tree. So if my, another way to talk about it, actually, if you have this picture earlier, which we're definitely going to come back here anyway, is that, for example, in this particular picture, the average tree T bar has a total of 12 nodes, but then T1 only have 8 nodes. So what you have to do is to say that based on how T1 is mapped to T hat, which is average, I am going to duplicate some of those nodes. Okay. So, so for example, let's see. Right. So let me see here. Yeah. So for example, if I look at the particular column in the input tree T1, it has node 6, and node 6 is correspondingly mapped to both node 1 and node 6 of the average tree. And where is node 1? Yeah, so node 1 and node 6 are both here from the average tree. This is node 1 and node 6. So what did that mean? That means that in the original tree at this node 6, I'm going to label it both at 1 at 6. So in some sense, I'm making 2 copies of this, right? So this is basically what's called blow up, meaning that I'm going to make the tree 1 to be as large as the average tree, and then by duplicating some of its nodes. So it's carry over the exactly same number of labels from the average tree, okay? So this is how you make them of the same size, but also at the same time, because of those coupling, it gives the correspondences between the corresponding nodes. So when I linearize them, they become correspondences between the dimension of those high dimensional vector, okay? All right, let's again going back to the pipeline. Okay, so once you actually bring every input tree to be a tree of the same size as the average tree, then to kind of make it into a high dimensional vector, really the keyword is flattening. You just take the weight matrices now, because every tree now is of the same size with the same number of nodes, then the matrix, the blow up distance matrix is now n by n, where n is the size of the average tree. Then you can just linearize it by taking each row of this matrix and concat them together. That become the high dimensional vector representing the tree. So that's step 2. And now what we have is to say, okay, so now all the trees is going to map into a column of this matrix. And now we're going to do matrix sketching. So we have formulated A, and then we are going to use different sketching techniques. And there's 2 classes of sketching techniques. One is column selection, which means that the basis of matrix B is formulated by columns that is selected from the original matrix A. So they are selected columns. And then second one is factorization. But both type of sketching technique is really focusing on the fact that it's trying to minimize. The first one for column selection is to try to find a projection direction of those columns such that it's minimized, A minus the projection of A along that direction, the Frobenius norm between them. Okay. The second one is again also looking at A, and so in this way, this is basically a hat. Okay. So both of them is really looking at sort of Frobenius norm differences between before and after sketching. And under column selection, there's 2 different types. One is called least length squared sampling, which is basically try to sample the columns proportional to square of their Euclidean norm. So you want to select like the columns from A that has high norm. Okay, so those are essentially like vectors that is in some sense more important. So you want to select them as your basis. The second type is start with a random subset of k number of columns, and then each selected column is either kept or replaced with another column based on the residual after all the other selected columns are factored out. Okay, so again, on the very high level, from the LSS, which is length square sampling, is basically saying that I'm going to sample the column based on the norm, and I'm going to choose the ones with high norm first. The second one is to say I'm going to start with k random columns and I'm going to replace those columns again based on some residual factorization. The last one is NMF, which is non-negative matrix factorization. It's trying to figure out a factorization of the matrix through B and Y, where now the basis in B is not necessarily coming from the original matrix. So in a way that in this framework, in one component, that in the column subset selection, the basis tree are really element from the original input, versus in the NMF, the basis tree are really new trees that you have not seen before, okay? So now once you have done the sketching, then the next step is to try to reconstruct the sketched merge trees. So those, remember I have matrix A, which is now approximated by matrix A hat. And then there's a corresponding column in A hat, that is AI hat and AI lowercase. So I want to turn AI hat back into a merge tree again. So remember, originally AI is a linearization of a weight matrix. Now, what I can do is I take this high dimensional vector AI hat and make it back into a square matrix, okay? So this is called WI hat. So what that means is that I take this long thing and I kind of reverse the linearization process by basically taking every n chunk of it and then formulated it back into a matrix form. Okay, so that become again back into a square matrix, and treating that square matrix as a weight matrix. And then what we do is we compute the minimum spanning tree based on these weights. What does that mean? So because this is a weight matrix, what it tells me is between node I and node J, what is the corresponding weights? So when I say I'm going to compute, for example, minimum spanning tree, it means I'm going to connect the node with one another that has the smallest weight first, which means they're the ones that is closest to each other in the original merge tree structure. Okay, so this is what you do is minimum spanning tree again is you have a bunch of nodes, you have pairwise distances, right? And you look at the tree that connect the nodes together that has the smallest cost. Okay. And then there's some more technical things is that, remember, I have blown up this original tree to be something much larger. So even if I compute the minimum spanning tree here, I'm going to get a tree that is pretty large. So then the last step, which is some technical step, is you need to simplify it quite a bit, because part of it is, remember, you have duplicated some nodes when you initially blow up the tree, right? So what's going to happen is that if you compute the minimum spanning tree, you're going to get some tree structure that would look like this. Okay, and what happened is that because those nodes, which I just put into the circle, are the ones that are very close to each other, and then that is essentially an artifact because I have duplicated some nodes in the original process. So I need to simplify it to get back to a tree of a similar size as the original input tree. Okay, and you can do the same thing with the basis tree, but there's something we can cheat a little bit. If my original sketching technique is selecting columns, which is CSS, column subset selection, then I actually don't need to convert the high dimensional vector bj back to a tree, because they are coming from original input trees. So you can just recover the corresponding column that you selected and what is the tree it comes from, right? Because you're just doing column selection, so your basis tree is a member of the original input. However, if you are using the matrix factorization, where the basis vector now from each of those columns in matrix B, each of those columns is now corresponding to a brand new tree that you have not seen before. So again, you are going to apply what's called minimum spanning tree to this matrix to recover a tree structure. So there's one thing I mentioned that, but I didn't have too much go into detail, is that minimum spanning tree is just one type of spanning tree. So the definition of a spanning tree is basically a tree that connects all the nodes in your data. But minimum spanning tree is the one that minimizes the total cost. But there's a different type of spanning tree, which is called low stretch spanning tree, which is the one that when I connect the nodes, I introduce the least amount of distance distortion to many of those distances. So we also did experiment with that, but it turns out in practice, minimum spanning tree actually works quite well. Low stretch spanning tree has more theoretical properties, but in fact, this is the first time we actually have a full working implementation of the low stretch spanning tree. So just to keep in mind here, you also have various choices of how you convert a particular pairwise distances, which is a hat, back into a tree structure. You can use different variants of spanning tree. All right, so now you've seen this. The last bit is talking about the arrow, right? Because remember, this arrow tells me essentially what are the outliers with respect to given chosen basis. The one with the high sketch arrow or high GW loss are the ones that can be considered outliers. So the classic thing coming directly out of matrix sketching is what I call the global sketch arrow. And the global sketch arrow right here is essentially the Frobenius norm between the matrix, data matrix A and A hat before and after sketching. So this is a global measurement, okay? And and correspondingly, there's local measurement, which is for every single tree, what is the difference between, what is L2 norm difference between the corresponding previous vector versus the sketch vector. So previous column and the sketch column, okay? And then with a simple arithmetic, you know that if I sum over the arrow, every single column, that gives me the global sketch arrow. So when I think about outliers are the ones that has high sketch arrow, meaning that that particular one is not sketched well with respect to a given basis. Okay. Now there is what's called element-wise or column-wise GW loss. What is that? That is basically saying that after I input a bunch of tree and I look at this corresponding sketch tree, I want to look at the GW distance between those two, right? So this is a way of measure the distances between the original tree and its sketched tree, okay? Using the GW framework. And then the global GW loss is the one that sums them all together. So you can consider that there is essentially two types of outliers. The outlier that has a very high GW loss, or the outlier that has a high sketch arrow, okay? And then those are slightly different, but oftentimes you will see trees that has a high sketch arrow, but also has a high GW loss, okay? But they capture very different things, okay? And also you might see a scenario where there is very small sketch arrow, but structure-wise, they are very different, which means they have a high GW. So another way to think about it, GW is really measures the differences between the tree structure, and then the sketch arrow is measures the differences between their corresponding matrix representation. So they are related to each other, but they are not identical. Okay? Any questions so far? Okay? So now what I want to get back to actually is the GW framework, because this is the most mathematical framework in this whole process. And I feel like we didn't spend that enough time on this. So again, getting back to, in this particular case, first of all, remember we defined what's called an average tree. So by definition, if I have a bunch of trees, the average tree, in this case, I can generalize this to graphs. If I have a bunch of input graph, the average graph is the one that minimizes the GW, is the one that minimizes the GW distances. Okay, so essentially you're looking at, I'm going to try to find an average, in this case, to be the ones that look at the space of all possible merge trees, the one that minimize the sum of GW distances. So this is achieved through a gradient descent framework, which is optimization. And typically, it's very much dependent on your initialization. So you will end up getting to a local minimum that minimizes the sum of GW distances. But it's not guaranteed to be a global minimum, okay? So sometimes the matching you get will not be perfect between. Okay, so, but let's say I have a way to actually compute the average. Then the next thing is try to couple every single input tree to this average tree. So to couple a pair of tree structure, or in this case, a pair of graph structure in general, is basically try to find the coupling that minimize the total cost. So really, the first thing we want to look at is what they call GW discrepancy, is you look at all possible coupling. Remember, the coupling is really just those kind of matrices, right? So essentially, you want to look at all possible couplings to find the one that minimizes total cost, which is quantified by something called distortion. So the most mathematical component of this formula is really how do I define this distortion? The distortion is basically saying that, well, if I map I from the first network, node I from the first network. So let's have a picture here. If I map node I, this is the first network or first merge tree. This is second merge tree. Let's say T1, T2, and I, K, L. So if I map node I from the first tree to node K from the second tree, and node J from the first tree and to node L from the second tree, I'm looking at essentially this term is looking at the multiplication of the coupling probability between those two. And then this first term here is capturing the differences essentially, or the loss between the corresponding weights. So it's basically because the endpoint of those two edges are mapped into one another, what I would like to see is what is the difference between their corresponding weights of those two edges. Okay, so that is what this loss function is. So W1 and W2 is really capturing what is the corresponding weights between them. And specifically, you can use a simple formula, which is just the difference between their weight squared. So that's what this formula is. If I substitute this new loss function into equation 1, you get actually what we end up doing, which is you take the weight differences between two of them squared, that became how much loss you get. So in a way that this loss function, if you imagine I match two edges, one edge from the first tree to an edge from the second tree, that if the endpoint match to each other and if their weights differences is very small, that specifically is a good matching for this pair of edges. Okay. So again, in order to compute the GW distance, we will be focused on this minimization process, is to try to figure out the best coupling between the nodes, which is basically the probabilistic matching between the nodes, such that this cost or this distortion is minimized. That's what gives you this corresponding picture here, right? This gives you the corresponding picture of how each of those input tree is mapped or it's probabilistic matched to the nodes of the average tree. Okay, so that's what the mathematical framework is for the GW framework. So now let's look at some real world examples, right? So this is all looks great in theory. It actually takes quite a bit to actually engineer this, okay? So I just want to emphasize for the rotated Gaussian example, if you choose corresponding columns, you will choose, those two columns that is in this green box that captures the variability among the underlying data. But then if you use factorization, which means in this case, I'm creating new trees, then the new trees are looking quite similar to those independent columns you just selected, even though those new trees are generated as, they're not coming from the columns. So it's very interesting that, what this is really saying is that, well, even if I'm using a non-negative matrix factorization to try to find new bases, the new bases that we select actually resemble very much as a basis as if you were chosen, as if they were chosen from the original input. Okay. All right, so new results. Let's go back to the first data. And also, I think I kind of described quickly how do you choose K. And then this is sort of like a black magic. It's a technique that people use for K-means clustering too, to try to find what is the optimal number of clusters. It's essentially saying that if I plot, this is a global loss, GW loss, and then this is a sketch error. Remember, those are two different types of global error measurement. And then essentially what you're looking for is try to find the elbow of those curves, which is basically, I see as I increase number of bases, I'm going to decrease the sketch error or the global GW loss. And the elbow is exactly where the sort of the arrow doesn't change drastically, right? That's where the elbow is. So for all those three data sets, what we do is we try to find the elbow in those curves to find the optimal K, which is number of bases. So for the first data set, you see that for both sketch error and for the GW loss, the optimal basis is actually 3. That is where the elbow is for both type of error. The second data set is roughly where there's 15 bases. And then last data set is much more complicated. So, to be honest, we don't really have a good elbow to look for. So we kind of just decided that 30 is the number of bases we're going to use. Okay. So this one is not very clear to us. There is a good elbow right now. All right, so let's look at the first data set. The first data set is some sort of flow. It's called heated cylinder. So it's a scientific simulation where the things are going, there's a flow coming from the bottom and to the top. And what you see here is in A is all those 3 bases. Remember, I'm using LSS, which means I'm choosing existing columns. So what happened here is that I would choose 3 columns, and this is a data set that has 31 instances. And if you actually look at the basis tree that we choose, they actually capture interesting topological changes in there. So if you actually compare tree 3 and tree 12, the difference between them is actually in tree 12, there is a pair of critical points that show up. Everything else looks roughly the same as original tree 3. So if you compare 3 and 12, there's additional pair of critical points right here in the tree merge tree. And if you compare tree 12 to tree 20, which is another basis that we choose, again, you see this addition of critical points. And correspondingly, we can also go back to the original input, and you can see exactly where those pairs of critical points appear and disappear. For example, remember going from tree 3 to tree 12, there is appearances of critical points. So that is this region of the domain to this region of the domain, which corresponding to a pair of critical points show up in my merge tree. And from here to here, again, there is the region C versus region D, there is a pair of critical points showing up. So in a way that this is just an indication that, first of all, my 3 bases is my optimal number of bases, and those 3 basis trees are good representatives of the underlying topology, okay? Now, the next thing we want to just show that for a particular tree, what happened to the original high dimensional vector representation and the sketched version. So remember, this is a weight matrix of the original tree. This is tree, I forgot, this is maybe tree 22, but this is a particular tree using those 3 bases. And you see that this is a weight matrix, so which means that every single entry here corresponding to distances between node 2 and node 10. So this is a pairwise weight matrix. And then this is a weight matrix after sketching. So in a way that if I linearize this is my A, and then this is my A hat, AI, and then this is my AI hat. AI means which tree I'm looking at. So now if you can see from a high level, you can see that, well, there is some structure similarities between those 2 matrices, right? Which when you linearize them, they are high dimensional vectors. But there's also a bit of a structure differences. So similarity, if you look at, for example, in this area, they all look the same. They have some sort of block structure. There is this nice block structure still preserved, like, for example, let me use a different color. You see like around here, there is still some sort of nice block structure in there, but then there are some variabilities between them. That is a result of sketching, okay? So, but now how does the tree looks like? The tree looks like the following. So now this is where I think is the most exciting part. Remember, the motivation of this project is I want to do sketching, but instead of sketching high dimensional vector, I actually want to sketch a very complicated structure, in this case, a merge tree. So I actually want to look at the tree before and after this framework. So if you actually look at this, right down here, the top, everything in the blue box is the original input merge tree. Everything that is in the red box is a sketched tree, meaning that they are, in some sense, their corresponding matrix vectors are linear combination of those 3 bases. And then you can actually look at before and after sketching. And for example, in this case, if you look at tree 7, before and after sketching, there's actually not even any differences between and after, meaning that they are really highly preserved using those 3 bases. The second tree 8, before and after sketching, you see there's small tiny differences. The first, all this area, all this looks very similar with one another, but then there is a minor difference right here, because if you actually look at here and here, there is sort of like a noise branch right here. So this is not in the original tree, but it's kind of showed up in the sketch. What does this mean? This means that, you know, it's not perfect in preserving all the structures. Okay, 15, again, if you look at 15, again, you don't see too much structure differences before and after. Maybe around those nodes, those 2 leaf nodes, before one of them is slightly higher than the other one, versus here, they are almost of the same height. But everything else look the same. Again, now if you look at 24, again, most part of the tree looks the same, except for this kind of branch right here, is that, for example, along here, originally I have 2 root nodes, but when I sketched, this top 2 root nodes kind of merged into like sort of 3-way branching versus a 2-way branching. And here, again, in this case, I have a little bit extra feature, which is really not, you know, as a result of the sketching, not be perfectly approximating. Finally, when you look at this last one, it's the same thing. Most part of the tree is well sketched, except for this area as well. Okay. So what you can see is that using just 3 basis tree, I can sort of sketch my underlying data pretty well. I mean, they're not perfect, right? But they are sort of close enough. But now if you notice tree 8 and tree 24 and go back to this picture here. So if you look at this picture, right, just look at the top one where the orange columns are the columns that is chosen to be the orange columns are the ones that are corresponding to my basis trees. And then the rest, if you see those nice blocked structure of yellow and green color, those nice block structure basically is telling us among all the 31 instances of my input tree, they can roughly be clustered based on their coefficient with respect to each of the bases. So there's really 3 groups or 3 clusters of tree who share similar structures with respect to the chosen bases. But what's interesting about it is also when I look at the arrow, this is element-wise arrow for both sketch arrow and the GW loss. So if you look at tree 8, right, tree 8 is what I show to have some structure variations. And 7 is the one that the sketched result is almost indistinguishable before and after sketching. So 7 has a relatively low sketch arrow and GW loss, while 8 has a pretty high element-wise sketch arrow and loss. Same thing with 24. So that's why when you look at this, when you look at those trees for 24 and for 8, you see a lot more structure changes because those are the ones that has some error in the sketching process. And if this error is very high, they will be corresponding to some sort of outlier with respect to the chosen basis. All right, you can also do the same thing, except, you know, I can use, now remember here, this is using one type of column selection method. Remember, in a lot of matrix sketching framework, the algorithm also can be stochastic, meaning that each time you change the random seed, you will choose a different set of bases. So for example, in this case, if I use a different column selection, and then I will get 3 different trees, basis trees that is not the same basis as before. But again, if you look at the structure, you will still see that those 3 columns, even though they are not, you know, in the original one, they are chosen 3, 12, and 20. Here, instead, I'm choosing the tree 2, 10, and 27. But if you actually look at the structure, like those structured variations among this new set using a new column selection method, is still not too different from the previous column selection method in terms of structure and in terms of how trees are clustered into 3 clusters, okay? And finally, the most interesting part is now, let's say I'm using 3 bases, except that I want to create new trees, right? So those are not coming from original columns, those are coming from matrix factorization. And then this is actually the corresponding basis tree you choose if you're using matrix factorization. So those are not elements from the input tree, those are new trees I generate. But interesting enough, if you actually look at the structure, they are also quite interesting. They are also very similar to the trees that is coming from column selection with some variations. If you look at how the structure looks like, right, there's some interesting branches here and there, but overall they have quite a bit of a good structure representation of the underlying input as well. And if you roughly see the block structure, there's again some block structures with respect to those 3 bases. Okay, so this is also indicative if you actually look at this picture here, right? If you look at the first picture, if I'm using NMF for this data, the overall loss, GW loss isn't very good, but the sketch error is actually quite good compared to the other method. So maybe the structure doesn't preserve as well as other 2 methods, but the sketch error actually converge roughly the same way. So this is sort of, if you look at individual ones, this is also a bit indicative where this area, right, they're not very bright yellow. So they have element-wise, they have slightly, they would have slightly higher error using the non-matrix factorization. All right, then the last data we have, this particular data set has 100 instances. And then this is a, this is second data set that has 100 instances. And this corresponding to this picture right here on the upper right corner. So again, you have a flow coming from left and it goes around to the right. And then you look at the merge tree of this flow field, which is using the magnitude. So now in this case, I have 100 instances. And you can compare to say that, remember this, when I choose optimal K, I say 15 bases is the best basis versus 10. If you look at, if I just using 10 bases, there is this red area, which is not very well sketched. That's precisely where when we choose additional 5 bases, they kind of cover those areas. So again, what we want to look at is what are the tree that we choose from column selection and how do they look like. So the top are basically all the bases that we choose, right? So you see that, again, with adjacent bases that you choose, you see some structure variations between them. So in some sense, again, all this is just showing that the basis tree we choose has sort of captures the structure variability among the input and give good representations. And then the next thing you want to focus on is to see how well are the sketch results if I were going to use 15 bases. And this is how they look like. Of course, this is a picture of the scalar field itself, but then what you want to focus on is actually the sketch result. Some of them has large sketch error, which means the sketch result have some noticeable structure difference, and some of them don't. For example, if you look at tree 4 right here is the one that don't really have much of a sketch error, which means that the structure before and after sketching doesn't change much. And tree 99 or tree 44, again, we are going to give multiple examples of the one. Oh, tree 7, for example, is the one with a high sketch error. So you want to see how the structure changes. So again, we give multiple examples here. So for example, tree 4, before and after sketching, the only difference is that around this node here, the function value change a little bit. Like in this area, the function value among those nodes change a little bit. Otherwise, the structure looks very similar. Tree 7 is the one that has a large sketch error. So you can see that actually before and after sketching, the tree structure changed quite drastically. Okay, so this is the one that is, in some sense, can be considered as an outlier. And for example, tree 99 is the one that has a small error in terms of sketching. you see that most part of the tree structure is similar, except around here, I become a two branching. This is a one-way branching. And right here in this neighborhood, I get some extra branches. But the rest of it actually looks very similar to each other. So again, what's interesting about this data set is that we have, 100 instances, and you can sketch it using 15 bases. Okay. And the last one is what we call the Red Sea data set. And Red Sea data set has so many topological changes that it turns out that 30 bases may not be enough. So you can also see this from the coefficient matrix. The coefficient matrix is showing that, each of those yellow, most of them corresponding to the bases that you choose. This is using 15 bases. This is using 30 bases. And you can see that in this whole area, in this red box, even if I'm using 15 bases or 30 bases, even in this case, I still don't get a very good representation of clustering, because in some sense, all the trees in here are represented as a linear combination of many of those bases. So you could expect that all this has a really, really high sketch error. However, yeah, go ahead.
When determining between 10 versus 15 bases, how far into the calculation of loss and sketching do you have to go before you can see that which one is better?
Oh, yeah. So if you go back, in order for us to determine what is optimal one, we actually plot this, right? We actually, so for example, for the first data set, we actually we start from 2 bases up until 10 bases, and to see whether there is elbow. And then in this particular case, elbow is at 3. So that's easy. Same thing from here. This one has, remember, this one has 99. This data set has, 100 instances. You go from, 5 until up to like 40 to see whether there is elbow. This particular one, we actually didn't go. This one only have 60 instances. So we went all the way to 40. And for this particular data set, we actually did not see an elbow specifically. So we just choose somewhere we think is reasonable and want to see how well it is under this particular choice. So for this last data set, we actually did not specifically see a really good elbow. Does that answer the question?
Yes, they said thank you.
Okay. All right, so yeah, so this is the last data set which we don't think the sketching is going to work well, just because there's too many structure variability in the data set itself. But we're curious because, if the column selection doesn't sketch well, what about non-matrix factorization? So that's what we did. We look at non-matrix factorization. Remember, those are going to be the new trees. Those are not selected from original tree. But, I would argue that it's slightly better. You see some bit of a block structure if I choose some new 30 bases. And then we want to look into the sketch result, okay? And surprisingly, the sketch result is actually quite meaningful. So even if with 30 bases using non-matrix factorization, this is how the tree looks like. This is tree 1 before sketching. This is after sketching. If you do them side by side, you see that this area looks identical. This area almost identical, except that if you look at this area, things got sort of switched a little bit. Same thing with this bottom here. This is a two-way branching. This has an extra, tiny branch right here. This also has a lot to do with the final smoothing techniques. Remember, I need to turn a large tree back to a smaller tree. So this may be some artifact over the smoothing. But still, if you look at this with 15 bases, even though we know that, with 30 bases, even though we know 30 bases may not be the best number of bases, but you can see that for some tree, the sketch result is actually quite good still. And again, this is another tree. This is tree 2. You see, again, there's some structure variations around where I'm pointing. But overall, like you actually see that there's part of this tree that is still very well sketched right here. Same thing with this tree here, right? You see some structure similarities. So in a sense that even though 30 bases may not be the best basis, you are still seeing a pretty good sketch result. So I think this is, for me, very exciting, because essentially now we can use the matrix sketching to approximate a large collection of complicated structures. So we have some other ongoing work, which is how to apply this to other topological descriptors. You should be familiar by now. There's also contour tree, rib graph, more smell graphs. The same framework should be able to apply there. And of course, there is a bit of a gap between theoretical understanding of sketched trees, because remember, matrix sketching, if we go back to the arrow assumption here, and then this is sort of the shortcoming of matrix sketching. Matrix sketching usually look at minimizing the global error, meaning that before and after sketching, the Frobenius norm of the entire matrix is tried to be minimized. However, it does not guarantee for every individual column of my matrix, I'm going to get the best sketching, right? So this is really all the existing matrix sketching technique is looking at minimize global error, but it does not guarantee to minimize individual ones. So some of them is well sketched and some of them is not. Okay, I'm not sure how easy it is to resolve it, or is it even possible to resolve it, which means I want to do sketching so that I also reduce individual columns errors. I'm a little bit pessimistic about this because it's not clear I can guarantee column-wise reduced error. Okay, so that's one theoretical gap. And then the last one is that we also talk about using minimum spanning tree versus other type of spanning tree. We know which one works well in practice, but we don't really have a theoretical justification to say it's guaranteed to work well. There's also various matrix sketching techniques that we just choose a few from the library, and then each of the sketching technique will have a different kind of practical results, right? But still, this is a very interesting application of really on the high level combine randomized linear algebra, which is matrix sketching, come from with studying of topology. Okay. All right. So that's that for the first part of today's lecture. Then the second part, well, again, I'm running. Second part, I actually want to spend some time talking about future direction discussions. And if we don't finish all of them today, we can continue for the next two lectures. After our guest lecture, we can continue having this conversation. So I want you to start thinking about, right? We learned a bunch of tools in this class. There's persistent homology. Largely, there are two underlying sort of umbrella. One is persistent homology, right? Persistent diagram. And one is those topological structures, which are things like merge tree, more smell diagram, more smell complexes, rib graph, contour tree, right? Those are topological. Sometimes some people call them topological structures. Some people call them topological descriptors. Okay, so I want to know that what is the most valuable tool you have learned in this class, and what is on your wish list, right? After you've seen the development, what do you wish to see? And finally, what do you think are the future directions for topological data analysis, right? Based on what we see and what you are most excited about. Okay, so open floor for discussion. Among those three questions, feel free to type or unmute yourself. And I want to spend the next few minutes to discuss this. Any takers?
I guess this is kind of along those lines, but I think especially since I'm pretty sure everybody's done the most recent assignment, I also had a very similar issue as the other Jordan, or at least what she posted on Piazza, that the persistent scale space kernel was seemingly much less accurate, and took I would often have convergence problems where it wouldn't converge after 100 million iterations. So is there a better implementation, or is there a really efficient way, or is that method just not one of the better SVM kernel methods?
Okay, so your question is basically going to the future direction, right? Are there better kernels?
Yeah.
That encode topology, right? So So I want to point it out, right? It's, this is actually one open question. There is actually a zoo of kernels, right? So if you actually look at, I will post it over announcement. I think there is a Python implementation of a number of kernels. Some of them I did not go into detail in this class. For example, there's persistent Fisher kernel and so on. There's at least 4 or 5 different kernels that has been implemented. And one of the open question actually is, what are the strengths and weaknesses of the existing kernels, right? So what I would say is that, well, if you want to kind of challenge yourself a bit more, if the persistent scale space kernel did not work for your given problem, would a different kernel perform better? Right? So this is really going back to this sort of comparative study of kernels, right? Is that, among all the existing 4 or 5 different kind of kernel, which one perform best for the particular problem you have? Does that make sense?
Yeah.
Yeah, so
Definitely.
I think this is a very interesting direction. Like I said, a few years ago, I heard the conjecture that there's a conjecture to say there's really not much of a variability among the kernels, even though if you switch from one kernel to another, that it should have a similar behavior. But that is just a conjecture. It was not supported by experimental evidence, right? So it's actually quite interesting to look at which kernel works best and for what problems. Okay. I think that's a very good point, right? But again, I want to emphasize that if you're using topological kernels in your sort of machine learning problem, classification regression, you have to be careful. Again, this is sort of like, I have a hammer, I want to find a nail kind of philosophy, right? I mean, to some degree, we always tend to do that, right? If I have a deep learning framework that works well for classifying animal images, I'm always curious whether that can be applied directly to medical images. And the answer is usually no, because you have to retrain your model. But, it's the same thing. Topology provide a collection of tools you can use for your data analysis. But there is sometimes a tendency, once you know this hammer, you want to see, okay, can this hammer hit all the nails I can find? So that is where, we actually did some sort of study, basically saying that for certain problem, if you just using topology tools, it's not sufficient, right? The topology is just a tool that is in your toolbox. And oftentimes you might have to combine it with something else to really improve your solution in a way. So I think it's always good to keep that in mind, because really topology data analysis, at least right now, how we know it by itself would not cure cancer, right? So you can't, that's more of an extreme statement, but I think it's always good to be cautious of the extent of the power of topology tool by themselves. Okay, so I think oftentimes it will give a new perspective over the type of problem you're looking at. Because, from the beginning, the first lecture we have from the semester, we say that, data always has shape, and shape does matter. And topology and geometry are one of those important tools used to describe the shape of the data, but it's not the complete thing. So because we're doing that, I think one very interesting direction that people has been looking at a lot is basically, right, we talk about TDA plus something. And then this something can be application, or it can be other domains, for example, statistics, right? Because if you think about it, in my mind, statistics is sort of thinking about numbers, thinking about numerical values, thinking about distribution, thinking about quantiles, thinking about confidence intervals, and so on and so forth. And then there's interesting combination of TDA and statistics, right? So anyway, great. Anybody else?
I have a question that kind of ties into what you just said.
Yep.
So say we're just starting with some arbitrary data and we want to solve some problems. So my question is 2 parts. 1, how do you know that TDA would work at all for this data? And 2, if you suspect that it would, which method would you choose, like persistent diagrams or reconstruct filtration? Like even with the MPEG-7 data, we use TDA because that's what the assignment wanted us to do. But with the MPEG-7 data in the assignment.
Oh yeah, the image, those black and white image data, yeah?
Yeah, so we use TDA because that's what the assignment wanted us to, but if that wasn't a given, how would we know that this is what to do and perhaps this would work? I mean, we could try everything, but typically that's too wasteful in terms of time. So what sort of guides using?
Yeah, so I would say the general guideline is the following. First of all, well, so for the image data, it's naturally very geometric and topological, right? Because it's shapes. It's a two-dimensional shape you can actually see, or three-dimensional shape you can actually see. So when TDA first started, a lot of applications of TDA is actually on lower dimensional data set like this, point cloud data set like this. So in a way that, for example, like if you expanded TDA there's a rising number of application of using TDA to study material science. Because if you think about the material, like if I take a X-ray image of some material, if you take a modeling of, say, diffusion process into the rock, all those are inherently 2D and 3-dimensional data set, mostly 3D, right? So there is actually a rising number of applications of TDA in material science precisely because those are tangible shapes that people study. So I suspect sort of topological data analysis to be very widely applied in that domain. Okay, so that's why the image data set, it's very natural to try it. Okay, now there is this two directions. One, if I have high dimensional point cloud that I don't really have a good way to visualize, how would I expect topological data analysis to be useful for that case? That's one question. Two is that if I have a data set, what if some other traditional techniques is going to work well already, right? So let me start with the second question. If I have this image data set given to me, and I was not exposed to TDA and at all, right? Then what would I do? Like one notion I would want to do is maybe taking each of the image and convert it to some sort of feature vector, right? And then you just feed that feature vector to SVM. Okay, so then the answer would be that, first of all, the first guideline is that is my data has some inherent topological or geometric properties that you believe TDA might benefit, and that's where you can apply that techniques. And two, if you don't know much about this data, the first thing you want to see is, does my traditional technique work pretty well already? And then you want to say there's this exploratory stage is, does topological data analysis help me to push it further, right? In the example of, say, brain networks, right? Brain networks comes as coefficient matrices. So people have been using that coefficient matrices for a long time, just, by itself. Like I'm just going to linearize coefficient matrices and do my machine learning tasks, classification, regression. And they work quite well, actually, right? But then the motivation of us trying topology on it is because the network itself, if you think about network, it's a graph. What is graph? What is network? It's about connectivity. What is connectivity? Connectivity is inherently topology, right? Zero-dimensional homology is about connected components. One-dimensional homology is about loops, and it's in some sense a higher order of connectivity, right? So in a sense, there's a natural inherent topology to sort of study of networks and graphs. So that seems to be a natural thing to try in addition to classic features to say, now let me add topology feature to see I can improve it, right? So now if I have a high dimensional point cloud, which I don't really know what's the shape of it, okay? Then I would say, again, your first process is to basically consider TDA as one of those exploratory process itself, okay? And for example, one thing that why mapper technique is so widespread and has a company behind it is precisely for the fact that there's high dimensional data set where you directly apply, say, statistical methods, or sort of regression across the entire set of data, you will not pick out fine level details among the subpopulation. The whole reason mapper algorithm is so widely used in the way is that because it's actually trying to understand the organizational principle in sub area of your data. and then globally to give you a global representation of how different parts is connected globally, right? So in a way that, you can think about, that's why the mapper algorithm is actually really initially, when they're marketing it, it was marketed as an exploratory data analysis tool, meaning that it's a tool you can use in addition to some other classic techniques you apply to high dimensional data, but with the hope that it will give you something new that you don't see. And then this something new is very much about local organization among my high dimensional data, which is captured by topology. Right? But to go back to your initial question, I would not know initially when you give me a point cloud data that TDA is the right tool for it. Right? That's really a big unknown, because as I said, TDA is very much of an exploratory tool. But we do know there is a sub areas where TDA has many applications. Anything to do with shape, for example, when Liz gave her talk about shape morphing in biology, right? A lot of biological entities are naturally trees or graphs. For example, if you look at the root system of a plant, right? The root system is naturally a tree, right? That's why the end of the tree is called root, because the root itself is a tree structure. So actually almost 10 years ago, maybe now, maybe 15 years ago, that there is a startup company that started at Duke. I think the company might still be around. I forgot the name of it. But they are specifically trying to apply geometry and topology to study root system. Because what happened is that when you have multiple plants, and then the plants under different genotypes will have different root systems. And some of those root systems are very well adapted to drought, for example, and some of them are not, right? If you imagine, if you actually dig out a plant in the desert, I think the argument is their root system go really deep, because they have to kind of go really deep under the ground to try to find sources of water. Versus if you in a very humid area, some of those root systems are very flat and shallow, but it's widespread because they can collect ore. So anyway, so I think the company was basically focused on using geometry and topology to study root systems and to try to maybe engineer better plants or better crops that, for example, can be drought resistance, right? So this is one area that it find really, really good applications, even commercially, to have companies behind them. There's other examples, like I said, time series analysis. I still think there's a lot of space in that direction, right? Because again, what TDA does that is different from signal processing is signal processing typically just treat the one-dimensional signal as a one-dimensional signal and do sort of different kind of filters, Fourier analysis, and so on and so forth. Versus TDA has this sort of expansive applicability because you can turn this signal into a high-dimensional point cloud. And it's based on your window size, based on your gap, based on how you convert it to this high-dimensional point cloud, you can encode different information. And then in that high-dimensional point cloud space, you can do stuff that may not be achievable through regular signal processing, right? That's one area where, again, I think it's interesting. And also the area I mentioned already, material science, I think the area which visualization is actually really a large area where a lot of topology, I mean, I didn't spend too much time on visualization per se, but all the topological structures as mapper graph, contour tree, Morse small complexes, all those topological structures you've seen in this semester's lecture, they are widely used in the branch called scientific visualization. So all this, for example, today's lecture, the first part of today's lecture, right? We're looking at merge tree of scientific simulations and try to use that to try to detect outliers. So there's a lot of applications of TDA in visualization. Yeah, okay. All right, we are at the end of the hour, and I apologize. I just realized I forgot to give everybody a break today. I just keep talking. But we will continue this conversation because I think this is also a fun conversation to have. Once you have a good, my hope for this class is you're exposed to various topological tools. And I think it's useful to start thinking about, what is the strength and weakness of topological techniques? And when do you think it's applicable? And what are the next research directions, right? This is a graduate level advanced class. So I would like you to think in that direction. Like once you know this area, once you know the foundation of this area, let's talk about future directions. Okay. All right. We'll continue this conversation over the next 2 lectures after the guest lecture. So, and I will stay for another half hour today because I was not around on Tuesday. So if you have questions, feel free to stay. Okay. All right.